All right, welcome to our second video on motion of an object under a central force. Okay, in this video we're going to actually apply our results to a gravitational field and see how that affects the motion of planets and things like that. Okay, so let's get up to speed on where we were here. We had a system of equations that looked like this. Now I want to point something out here. In the setup that we have, what we're looking at is, remember, an object moving around in a force field, right? Now, if the object is moving in a direction parallel to the vector pointing back at the origin or outwards on that same line, then this problem is not interesting. All right, this is just a one-dimensional problem. It's just going to go up and then be pulled back down by that gravitational field, right? And we know how to explain that using Calc 1 techniques. That's not an interesting problem. So we are only interested in the case where the object has some velocity in some other direction, all right? And what that means is, so if our velocity is pointing in this direction, that means that theta prime is not equal to 0, okay? And actually, all we really need to know is that theta prime at time 0 is not equal to 0. And actually, from that, we can conclude that theta prime is never equal to 0. Why is that? Well, just knowing that it's not equal to 0 at time 0 tells us that, well, if this is non-zero, we know that r is not 0. We're not going to start at the source of the gravity. Then we're not going to move anywhere. So we know that's not 0. So if theta prime of 0 is not 0, that means the constant's not 0. But if this is a constant for any time, that means that theta prime can never be 0, right? Because it's a constant. So if it starts out 0, it has to stay non-zero. So that is a useful thing to know, and it also tells us that r must be a function of theta, because if theta prime is never equal to 0, it's never equal to 0, that means theta is always changing. And so the only way r would not be a function of theta is if r changed without theta changing. But if theta is always necessarily changing, that means that r can be thought of as a function of theta. So that's going to be something that's important to keep in, two important facts to keep in mind. One is h is non-zero, and r is always going to be a function of theta. Okay, so what we're going to do now is we're going to prove a claim. Okay, so what you'll see next is a claim that we're going to prove, and that claim is going to help us establish the results that we need for a gravitational field. Okay? What we're going to do is we're going to work towards a certain differential equation here, and we're going to try to prove something. We claim the following thing. Okay? We claim that if u equals 1 over r, then u is going to satisfy this differential equation. Okay, so this is something that we want to prove. We want to prove that if you let u equal 1 over r, then u satisfies this differential equation. When I write theta theta down here, that's the second derivative with respect to theta. Okay, now why is this useful for us? Well, if you look at this thing, it's the left-hand side is second derivative of u plus u equals some function, right? So this is, if you look at that side, that's similar to the differential equations we've been looking at recently. It looks a lot like the spring equation, right? Where we had two derivatives plus the function. So this is the type of differential equation that we know how to deal with. So this is kind of interesting. This means that we can probably use the techniques that we've learned so far to deal with this differential equation. All right? So let's go to a new sheet. Okay, so here we are. I rewrote the system of differential equations that we're looking at here, and we're going to try to get from this guy, right? So the first thing that we're going to look at is just this. I want us to realize that this thing, because h is a constant, and it's a non-zero constant, remember, that means that theta prime is never 0, right? So theta is always changing. And what that means is that we can view r as a function of theta, okay? So we're going to be, since this is a constant, right? So I just want to point out, this implies that r can be viewed as a function of theta. It's not like r can change without theta changing. Theta is always changing. That's what this is saying, right? So r is a function of theta. Okay, so what we're going to do is we're going to start computing these derivatives with this in mind, all right? So we're going to start, we want to get to the second derivative of r so we can plug that stuff in here. And we're going to try to write all this in terms of u. All right, so let's use what r is. Remember that u is 1 over r. That means r is 1 over u, or u to the negative 1. And so from that, we can compute r prime. R prime is this. Okay? But let's now remember the chain rule, right? So u prime is du dt. But the chain rule says that du dt is du d theta times d theta dt, right? Keeping in mind that u is also, because u is 1 over r and r is a function of theta, u is a function of theta, right? So this is du d theta times d theta dt. Okay, cool. We're getting our u thetas that we need, right? We need to get those. So that's good. Now we can say a little bit more here though, because we can use this differential, this equation up here. Theta prime is the same thing as h times r to the negative 2. But r to the negative 2 is the same thing as u squared, right? So this is the same as h times u squared. That u squared and this u squared are going to cancel each other out. Isn't that nice? Okay, now let's compute the second derivative of r. Well, we'll just start from here, right? We got a nice simple expression here. Let's use that. So h is a constant, so I'm just going to get this. Okay, but remember, we can use the chain rule again. The derivative with respect to time is the derivative with respect to theta times d theta dt, right? So this is but again, theta prime is equal to u squared h. Okay, so look at that. Okay, so what we're going to do is we're going to plug this stuff into this in up there, right? We're going to plug r double prime in. Okay, so let's see. Now I'm going to put this stuff up there. I'm subtracting theta prime squared times r. But remember, again, theta prime is just u squared h, right? So this is u to the 4th h squared times r. And r is u to the negative 1. Okay, so that's just this. And remember, r is 1 over u. Okay. Okay, let's simplify things here. Well, okay, that u and that u make a u cubed. And if I divide then by u squared, if I divide u by negative h squared u squared, what do I get? So I divided by negative h squared u squared. And I think we've achieved our goal here, right? Okay, I got it written a little bit. I just got the h and the u squared switched around. But yep, that's exactly what we were after. So great, we've proven that claim. Now, remember, like I said, this is important for us because this is like the spring equation almost, all right? So we're going to be using this to prove some cool results, all right? Okay, so here we are. We've proven this result, all right, where u is equal to 1 over r. remember. Okay, so we're going to use this result to describe the motion under a gravitational field. We haven't done none of the results that we've gotten so far have anything to do with a gravitational field. These are just any central force. Pushing inwards, pushing outwards, it doesn't even have to be gravity, just some central force, all right? So what we want to do is see how this works with respect to gravity, all right? So what we're going to do here is we're going to just look in a physics book and realize that gravity, the force due to gravity, is given by the gravitational constant multiplied by the product of the masses of the two objects involved, maybe the sun and the earth, right, divided by r squared. This comes from Newton's law of gravitational attraction, right? So it's proportional to 1 over r squared, the distance between, where r is the distance between the objects, right? So we have some object here with capital mass, capital M, and then some object over here with capital lowercase m, and the distance between them is r. And so this describes, if we multiply by this gravitational constant, this describes the gravitational attraction that little m feels by big M, okay? So that means that our force function, f of r, is equal to, that's what it is. If we were asking what was the force that the mass experiences, well, it's this, right? So, but it's remember that f of r has to be negative, right? To be pointing, to make sure our vector, our force vector that we defined, is pointing towards the origin. So it's actually going to be the negative of that. Okay, so that's what we get. Now, remember that u is 1 over r, so this is the same as this, right? Okay, so we're going to put this into here, right? So what's f of 1 over u, right? Well, if I put a 1 over u in place of, oh, I guess that's what I just did, right? I mean, when I said, yeah, so I just viewed this as a, right. I mean, plugging in 1 over u is the same thing as making that substitution, u equals 1 over r, right? So if I just, if I computed 1 over u in place of r, right, that I would have gotten the same thing. So what I've just found here is f of 1 over u. I just went about it a different way, okay? So that's that. So what do I get when I multiply that by this, right? So what's all this stuff? Well, let's see. It's this thing, right? That this part is this, right? So if I put that all together, well, the m's cancel, the lowercase m's cancel, the negatives cancel, right? I get g, oh, and the u squareds cancel, right? So I just get g capital M divided by h squared. That's it, right? Everything else cancels off, right? So I just have a constant. Wow, okay, it's just a constant. So that's what I was worried about. Like, how are we going to solve this differential equation? It's not even linear, right? Well, now it is, right? Now it's a linear differential equation. So, let me replace the thetas with primes. I know I was using prime to denote d by dt before, right? But now prime means d by d theta, okay? So let's just write that so that it looks familiar to what we saw before. Okay, this is differential equations that we've been dealing with for some time now, right? And so we know how to get us to a solution from here. Just get out of the way. So the solution, has the form. You can write it in this form. We've done some exercises. We've done some videos where we did that. That's the complementary part of the solution, right? Where you set this being equal to 0 and solve it, right? You write it in terms of sine and cosine, but then you can compress that and write it. And using some trig identities, you can just write it in terms of a single trig function, cosine. But then you have to solve the particular, you have to find the particular solution too. Well, that's just going to be I think it's pretty easy to see just by, oops, that should be an M, through observation that this works, right? Just, plug that in. That solves the differential equation, right? Gm over h squared, the constant, just plug it in here. It works, right? So that's the particular solution. So we got it. A and phi would be determined by initial conditions, right? If we were to specify them, okay? So what can we do with this? Well, remember that what we're really interested in is r. We want to know what the radius is at any given time. So let's get this back in terms of r. Well, u is 1 over r. So let's get that in here. So this is the same as 1 over r, right? So just reciprocate both sides, and you can write r as 1 over this, right? So 1 over this stuff. Okay, and now I'm going to multiply through. Let's set some new variables here. Let's let rho equal h squared over gm. I want to cancel this stuff out. And let's set e equal to, let's see, when I multiply this over here, I'm going to have an a times rho. So let's just let e equal a times rho. Okay, this is not Euler's constant, right? This is not the e 2.71828 blah blah blah. This is just a letter e. This is a variable that equals this. Okay, so don't confuse that. And so what I'm going to do is I'm going to multiply the numerator and denominator by rho. That's going to cancel this out and make a 1 here. And because of the because a times rho is e, this is just going to become an e. All right, so I'm going to have, and then a rho will hit the numerator as well. So this will just become e cosine theta minus phi plus 1. Okay, cool. All right. Well, what is this telling us? Well, check this out. Not this one. This guy. Here I plotted it. I plotted it in polar coordinates and Desmos. Okay, so I've got basically the same equation. I can't use lowercase e because it thinks it's Euler's number, and I used a p instead of a rho, but it's essentially the same thing. And you can see what these things do. If I change the rho, it changes the size of the orbit. If I change phi, look at this. I can change the angle of the orbit. Look at that. It just spins around. Okay. And what does E do? Well, this is interesting. So look at this. So when E is between, as E approaches 0, right? Look at that. It becomes a circle. So when E is 0, it's a circle. When E is between 0 and 1, it's an ellipse. But what happens when I go past 1? Look, it becomes a hyperbola. Right? So why is that? So this hyperbola is actually an interesting observation here. This is what would happen if an object was just flying by in outer space and just flew by our sun, like a meteor from another solar system or something, came into our solar system and just flew by. It's going too fast to go into orbit, but it's going to swing by. Remember, the source of gravitational attraction is right here. It's going to swing by and get affected by that and come and kind of catapult out, right? And so that's the hyperbolic solution. So we actually get to see some solutions maybe we weren't even expecting here. Of course, if the velocity is slow enough, it'll be in an elliptical orbit. And if you're really careful, you can get something into a circular orbit, right? The E is called the eccentricity of the solution here. So let's just make note of that. These are some interesting observations. The eccentricity, I think they're 2 C's. If E is less, well, remember, if E was 0, that corresponds to a circular orbit. If E is less than 1, then we're getting an elliptical orbit. And if E is greater than 1, we get a hyperbolic. It's not an orbit, so it's a hyperbolic curve, trajectory. But I wrote curve already. Curver. Hyperbolic curve. Okay? All right. So that, I think, is pretty much covers it here. Let me just make sure we didn't miss anything. Well, there is one other thing we can say here. So let me just point this one thing out. When we look at this picture, you can see there are two radii. Well, there's two special points on this ellipse. The maximum radius is the aphelion, and the smallest radius here is the perihelion. Okay, and so you can compute those if you just plug in the right values of. You just minimize this function and see where r is the smallest and where r is the biggest, and so just use some Calc 1 in here to figure that out, and you'll see that the minimum value of r is equal to rho over 1 plus e, and that corresponds to the perihelion, P-E-R-I, and the max is rho over 1 minus e. That's the aphelion distance. Okay, and these are relevant. What actually happens, there's something interesting that happens that Newtonian physics does not predict, and that is that what they have observed is that actually they observed this in Mercury, and they couldn't explain it for the longest time. Astronomers observed that the actual orbit of Mercury spins like this. And the Newtonian description of gravity does not predict that at all. So they were really confused about why that was happening. And it turns out that after Einstein's theory of relativity came along, they found out that that explained it perfectly. And that was one of the first verifications of Einstein's theory of relativity, was that, wow, it explains the perihelion shift of Mercury perfectly. Something that we've been searching for a solution for the longest time. And by the way, Einstein's theory, which he wasn't even trying to solve this problem, but it worked. It solved that perihelion shift problem, and now they know why it happens. It has to do with general relativity's curvature of space-time. All right, so that's it for this video. Hope you learned some stuff, and I'll catch you in the next video.